Hi everyone. So in the previous video, I realized that I did not clearly explain the differences between the types of policies and environments when computing expected values in the value function. So in this video, I will fix that and make the distinctions clear. So we have this system. In the first case, we have a deterministic environment and a deterministic policy. So this is our system. We have a reward of minus 0.1. This is not minus 1. There's a mistake here. We have 16 states and actions are left, right, up, down, gamma of 0.9. Right, the transition probability here is 1 for the intended state and 0 otherwise. Our policy is right if possible, else go down. So in this first case, both the environment and the policy both of them are deterministic. That means that the world behaves exactly as expected and the agent always knows what to do. So when the agent, for example, is in state 5, it checks the policy, which tells it go right if you can, otherwise go down. Since going right from state 5 leads it to state 6, and the environment is deterministic, the agent will always end up in state 6 from state 5. Okay, the reward in state 5 is minus 0.1, and the estimated value of state 6 is 0.72. I made this up, by the way. These are just random numbers, the values. So when computing the value of state 5 in the Bellman equation, all we have to do is the typical way, reward plus gamma times the value of the next state. Okay, so in this setup, everything is predictable, and so this is perfect for planning and value iteration. All right, let's look at the second case. Now we are going to be slowly introducing uncertainties. We have a deterministic environment and a stochastic policy. Okay, I hope this is clear. All right. Same setup. The only difference is that the policy is from a state, there's open to probability of going left, right, up, down. So this is a stochastic policy. In this second case, the environment is still deterministic. If the agent picks an action, it will end up in exactly one state. But now the policy is stochastic, I've already mentioned. This really means that the agent doesn't always pick the same action. Okay, there's some randomness. So the agent is currently in state 5. It wants to, from state 5, the agent chooses randomly among 4 possible actions, left, right, up, down, each with a probability of 0.25. Okay. Since the environment is deterministic, each action leads to a specific next state. So we compute the expected value of each action using the value of its resulting state. So from state 5, the agent can there's a probability of 0.25 it will end up in state 4 by going left. So we're going to take the value of state 4 times that probability 0.25. There's probability of 0.25 going right by going right, and the value it will end up in state 6. Value of state 6 is 0.72 multiplied by 0.25, and then we get this. We do that for all the 4 possible actions. Take the summation, multiply by gamma, add it with the reward. Okay, so in this case, the uncertainty comes from the agent itself. It's still figuring things out and trying every option equally. All right, let's introduce another scenario. All right, here we have stochastic environment, and a deterministic policy. Now, the situation flips. The agent always chooses the same action in each state. So this is like this is the deterministic policy, but the environment behaves unpredictably. So the difference comes here. There's 0.8 probability of the intended state and 0.1 probability of opposite of each of the two side directions. So from state 5, it wants to go 6. There's 0.8 probability, but there's 0.1 probability and it will end up in state 1. 0.1 probability it will end up in state 9. Okay, so we use those probabilities and the value estimate of all possible next state to compute the expected value. So from state 5, it wants to go right, and that intention is right is the intention, has a probability of 0.8. 0.8 times the value of the action resulting from going right, 0.72. We multiply that probability times that value, and 0.1 times it can flip and go here with probability of 0.1 times the value of state 1. And then similarly for this, we do that, we sum them up, multiply by gamma times the reward. All right, okay, I hope this is clear. So in this case, the randomness comes from the world. The agent knows what it wants, but the nature sometimes, the environment might have other plans. Okay, so far so good. I hope this is clear. All right, we have a stochastic environment and a stochastic policy. Now, this is like a double layer of uncertainty, right? Let me fix this. So we have the same probability that we saw before, 0.9, 0.8 for intended state, 0.1 for opposite each of the two side directions, 0 otherwise. The policy is from each state 0.25 for all the possible actions. So from a state, the agent kind of randomly chooses one of the 4 possible actions. It's currently in state 5, each with a probability of 0.2, and no matter what action it picks, the environment might take it to an unexpected direction. So for every action, left, right, up, down, what we need to do is, well, from here it can decide to go left. Well, the intention is go left, it will end up in state 4. State 4, when it intends to do something, it will achieve it with a probability of 0.8. We multiply by the value of that next state, and then for opposite directions, we take the probability times their values, right? It can end up here with 0.1 times the value of state 1. We do that, sum them up, then we weigh by the probability from the policy. Similarly, first it can decide to go right. The intention is going right. It will end up in state 6. Well, it will achieve that intention with the probability of 0.1, and it will end up in state 6 which has a value of 0.72. We multiply by the probability. We do that for all of each of the two side directions, then sum them up. We weigh by the policy. The policy of going right is 0.25. We repeat for all the actions. I hope this is clear. Yes, we do that. We weigh that by the policy, and then we compute total expected value across all these combinations. I mean, we do that, then we sum all the four values, multiply by gamma times the reward. The reward, by the way, here I wrote negative form, but it's really minus 0.1. Okay, so this setup, this case reflects real world learning. The agent is still exploring and the world is unpredictable, but even with this noise, value estimate can still guide the agent to make better decisions over time. All right, I think we are good. Thank you very much.